Hi guys, in this video I want to walk through this tower hopper problem from CS Dojo, and I will leave the problem in the link in description down below. But briefly, this is how what this problem looks like. So we are given an array of towers, and as you can see, we have a 4. In this example, we have 4, 2, 0, 0, 2, 0. The first two indicating the height of the first tower, the 2 indicating the height of the second tower, etc. And when we're standing at the top of the tower, we can jump, we can land to different locations. If the tower is higher, we can jump further in the distance. So, for example, if we are standing in the tower that has height of 4, and then we can jump to here. We can take the distance 1, and we can jump to here, and jump to here, and that's the maximum distance we can reach, because we are at a tower of a height of 4, and this is the farthest distance we can reach, and also we can reach any other towers or the land in between. And the goal is to jump off this the land. Jump off all these areas. So, for example, if we landed to this tower here, and we can at the height of these 2, we can jump 2 steps, and then we can jump off the whole thing. So the function is to figure out, is it possible to jump off this area or not? So for this specific example, it is possible, because we can jump to here from the first tower to this tower here, and then we jump again, and then we jump off, because in here we can jump at most 2 distances, and then we jump off the land. So I'm going to present the 2 solutions. One is the recursive function, which is a bit slow, because it takes a lot of reiterative or repeating steps. So it's not efficient, but it's good to use that to build up the intuition for the next solution, which is the dynamic programming, which is way more efficient and only takes a big O of n in the time complexity. Let's first take a look at the first solution first. So the function is called is hoppable, and we have a 2 lists initialized in here. One's the location, and basically this is indicating the index of the list. So we just have a 0, 1, 2, 3, 4, and 5 for this specific example. And then we have another list. It's called steps needed escape. So this is how many steps we need to escape from the area. So if we are standing in the first tower and we need 6 steps to fully escape. If the tower was high, it has a height of 6, it can just jump out from the area in 1 jump. And same idea for the last one in here. If there was a tower here as of a height of 1, and you can jump off from the area with only 1 jump. So this is what it means. And then we have a hop function that we will call recursively. We first have a condition checking. If the jumping off point is less than or equal to the length of this the tower's list -1, because we are looking at indexes. If that's the case, the reach distance is equal to the height of the tower, and this is the maximum distance we can reach for each of the jump for 1 jump. So for example, the reach distance when we're standing here will be 4, because this is the height of the tower, and then we can reach the maximum distance of 4. And if the reach distance is greater or equal to the step needed to escape, and then again, we are done. So we will return a true, because we can jump off from the area from that point. So basically, let's say if we're standing here and the reach distance is 2, and the needed the steps needed to escape is equal to 2 as well, because you can jump off from 1 and 2 and jump off the area, and then you will return the 2 because the game is because at this point we can jump off from the area. And however, if the reach distance equal to 0, so we are at the land, so there's no way to jump back to the tower anymore. So we basically stuck in their space. So we will return a false. So this is both of them is like a terminal point. And then we have a while loop that we will recursively call the hop function. We initialize a variable called escape, and with it's a Boolean variable, and then we initialize as a false. And then the jump distance equals to 1, while the jump distance is less than or equal to the reach distance. And we are not yet escaped from the area, and we will recursively call itself by jumping to different towers. So we are reaching to different towers by just increasing the jump distance from 1 all the way to the reachable distance. So for example, in the first tower, the jump distance will go all the way from 1, which will jump to this tower, and then 2 in this tower, in this land, and then 3 to here, the 4 will be here to this tower. So we have this while loop to recursively jump to different towers and then call the functions. The loop will be over until we can no longer reach to the further distance, or we can jump to a point where we can escape, and the loop will be over. And then because we are in the initial tower, that's why we just call the initial jumping point and then return that. This function definitely works. As you can see, if we input the tower in here, 420020 as the example that we went through, and then it will return a 2 because it jumps to this tower first and then jump off. And then if we have the tower for only 1 and 0, and you return a false, in this case it's a false as well, because at the initial jumping point, we can the furthest we can reach is here, 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 and here, and then we jump to here, the second tower, and there's no way we can escape. However, if we build one tower in the middle in here, you can jump to here, and then jump to here, and then jump to here and escape. So it's 2. So this function definitely works. However, this is very inefficient. We are recursively calling the function itself many times. So for example, when you look at here, and then we jump from this tower here, this is one computation, and let's say if we are in this tower here, and then we jump in here, jump to this tower again, and the same computation will perform again, because we call itself for the computation for the first time when we jump from the first tower to this tower, and then we perform the same computation when we are standing in this tower, and then jump 2 steps in here. So a lot of repetitive computation, which will return the same result, and we don't want that for this repetition, because it's making the computation very inefficient. And one way to solve this is to employ the dynamic programming, which I will show at this solution down below. So we have another function named is hoppable DP, and it's very similar setup as before. However, we have one more list. This name is named escape memo. So we initialize. So this has a memory that keep track of what tower allows us to escape from the area, and then we modify this hop function, which we will go through together later. And then in this while loop, we jump we're moving backward from the towers list, and then to record the is it jumpable or not for each point in time, for each point in the tower. So let's go back to this example here. So we will start from here, the last tower, and then to see if that's jumpable. Hoppable is not. And then we will go back to the prior step to see this one in here, this tower, is it can escape from the area? And the answer is yes, it is. So we're moving backward from the list of towers, and then to see and ask ourselves, is it possible to jump off from the area from that specific tower? So as an example, let's say initially we are at the last tower, which has the height of 0, and ask ourselves, is it possible to jump off the land? The answer is false. That's why we can fill up. This is how we can fill up this escape memo. So the last element will be a false, and then we move backward to this tower and ask ourselves, is it possible to jump off? The answer is yes. And then we will the next element will be a true, and then move backward again. Ask ourselves, is it possible to jump off? The answer is no. And here the answer is no again. And here the answer is yes, because we can jump to here, and then we can grab the answer from the list that we collected earlier, this escape memo, because we can jump to here, and then we look up the answer that we did before on the list, and then says yes, and then we go back again, and then we stand in here, and then we can jump to here, and then we look up the answer, which we can jump off from this building. This is the dynamic programming approach, and this hop function is a slight modification of the hop function that you saw earlier. This section is the same. However, for this section over here, this become is changed from the recursive calling of the hop function. Now we become the lookup, which takes only constant time. And then this statement here is keep recording the steps backward from the last tower to the second from the last, and then all the way to the first tower. So at each point we just move back one tower at a time, and then we return the initial state, escape memo 0, which is we are in the very first tower, and we will have an exact same answer as we saw earlier, but this is much faster. This only takes a big O of time, a big O of n. Instead of this one, it goes increase the time increase exponentially. And in terms of the space complexity, we have a location list and also steps needed, escape memo, and all of them takes a big O of n. So the space complexity is also linear. This is so much for my solution. I hope you like it. If you do, please help press the like button and subscribe to the channel. And I will see you in the next video. Thank you.